For my experiment, I rolled a mini soccer ball on a carpeted horizontal plane. As the ball rolled, a constant velocity was reached for a certain period of time, which I captured in 17 frames. For this duration, Newton's second law tells us that the ball had a net force of 0, and therefore no acceleration, causing a constant velocity in the positive x direction. As you can see, I chose the horizontal axis pointing to the right to be the positive x-axis. The outcome and the calculated numbers would not have changed if I had chosen another axis to represent the way the ball rolled, except that the vector location for the numbers would be in either the y or z spot, since I chose a Cartesian system of x, y, z. The direction would only have changed if I had flipped positive for negative direction. In each of the 17 frames, the point mass was located in the center of the ball, so that the displacement between each time change would be measured to give us the line graph on the top right. The line has a constant positive slope representing a constant positive velocity. From the data collected, we can get the initial position and the average velocity. The ball was initially at 0, 0, 0 meter. X, Y, and Z. Average velocity, or change in position over change in time, was calculated to be 1.52 meters per second. It's also 1.52 meters per second in the model because we set this. As we know, the velocity does not change throughout the entire lab because we are looking at a constant velocity. This is because the net force is 0. The net force is the total pushes and pulls acting on an object. In this case, the force of me pushing the ball was greater than the force of resistance or friction until a constant velocity was reached, where the force of my push was equivalent to the resistant forces. In addition to the video analysis, a computer programming file was created to model and predict the position of the ball at each time. The change in time was 0.01 seconds. A very small but necessary time change so that the predictions are more accurate. If delta t is small enough, changes in forces or other motion will be too small to make a difference, making a better approximation. This program greatly helps us to understand Newton's second law step by step in the context of this lab and lets us predict the position of the ball by only entering the ball's initial position and velocity, the ball's mass, and the change of time. From Newton himself, we know to have an acceleration, the net force must not equal 0. However, since our velocity is constant or not changing, we know F net is equal to 0. From the law, we know final velocity is equal to initial velocity plus acceleration times change in time. But since acceleration equals 0, final velocity equals initial velocity. Knowing this, we can continue to predict the position at each time using the formulas shown. Using the computer model, we were able to create a spreadsheet comparing the predicted positions to the experiment's positions in meters. The line graph illustrates this comparison with the model's position in red, with the experiments in blue. The slopes of each line seem to be quite similar, and both are definitely positive and straight, but a discrepancy does exist. The model predicts the positions to be higher than recorded fairly quickly. There could be many other explanations for this error, but most likely the velocity was not truly constant, meaning the net force was not truly 0. In the non-model, real world, a 0 net force is difficult to achieve, especially when rolling a ball on carpet. The friction may have been greater, or the ball not perfectly round, or my observations may not have been perfect. For any of these reasons, the velocity was not constant for the whole time, and appeared to slightly decrease. Overall, Newton's second law teaches us that force is everything. Without it, an object's motion cannot change. In order to have an acceleration, we need force. In order for a change in velocity, we need acceleration. Therefore, with our approximate net force of 0 here, we are able to observe an object with constant velocity and discover the relationship between physics and the motion of our everyday lives.